Thank you, James, for the kind introduction. My name is Simon. I'm here to present to you about the assessment of the ecological impact. I'm here for because Tim Lunch, my manager, couldn't be here today. Thanks to Formnext for having us. Thanks to 6K for the cooperation and the powder provided. And also thanks to my colleague Christian Weiss, who did all the hard work. I'm just here to present it to you today. As a quick motivation, why are we doing this? And I think most of this should probably be common knowledge by now. We are, if you take a look at the left side, we are using up way more resources and energy today than we actually should. So back in the 1970s, about 50 years ago, we used about as much energy and resources than the Earth could provide to us. By now, we are way past that point, and we need to get back to at least 1. On the right side, you see the emission by Germany per year. It's the emission, if you look at the left side, for industry, which would be about 20%, that is direct emission. And then also, if you take a look at the far right side, where the blue arrow is, that is emission due to electrical and heat production. And again, their industry takes up about 11%. So industry, we build parts, we produce something. So this is basically our emission that we need to drive down. In order to do that, we need to first assess what the main emitters are and where the biggest leverage is to make an improvement to these numbers. And that is where life cycle assessment comes in. The basic idea is to, for a given product, to assess what needs to be, or what emissions occur when you produce these by comparing the inputs, the outputs, and the next step then would be to assess what the ecological impact is, because using up 1 kilowatt hour of electricity, that doesn't mean much. The question is, how does that in turn then impact our planet? On the right side, you can see the practical approach for this case study. So we started by defining what we want to take a look at, because there's a lot of data you can possibly take a look at. So we defined what we want to include in this study. Then we took the inventory, which is basically gathering the raw data from the actual production process, and then assessing the impact of whatever we found on Earth or on our planet. For the LPBF process, it's basically the inputs on the left side, material, energy, and some others, and the outputs is, again, material, waste, heat, emissions, and whatnot. If we take a look at the process chain for laser powder bed fusion, especially the entire one, this is, of course, oversimplified, because you can think of thousands more emitters. For example, if you go from material extraction, this also needs to be transported somewhere. So you are going to have emissions to transport it. You are going to have emission to build the truck to transport it. So there's 1,000 factors that you technically should take into account, but at some point it just becomes impossible, which is why we, for this case study, opted to focus on the powder manufacturing and the AM process, especially since we wanted to see how that sustainable powder by 6K impacts this. And you can imagine that further down the line, for example, in application, if it's the same part, it doesn't really matter for the application or the emissions during the application, whether it was made from regular Inconel or from sustainable Inconel. So this is why we drew the system boundaries as they were. And then, of course, recycling is a very big topic, and Brett is going to shed some light on that right now.
Awesome. Thanks, Simon, very much. So why the collaboration? So first of all, for those that don't know, 6K is a powder manufacturer, and I'll get a little bit more into it. But obviously, Fraunhofer is a world-renowned institute that is trusted. So working with them was an obvious no-brainer for us. The industry itself and what's happening about sustainability has really changed. Our first coming out party as a company was 2019, and we've talked about it a lot this week, how the industry has actually changed in 4 years. People have this look on their face like, you guys use scrap? That's not going to be quality enough for me. There's no way that can work. That was 4 years ago. Now the amount of people that are coming to us because of it, it's really changed dramatically in 4 years. Also, you do see a lot of claims about sustainability in the industry. as well as outside the industry. And so there's a lot of greenwashing or small things that don't make a difference. What I really appreciate is how additive manufacturing really changes the game, as well as in combination with the use of our powder. So it was an obvious thing for us to collaborate with Fraunhofer, so we really appreciate it. For those that don't know, 6K is a powder manufacturer, and we do it in a little bit different way than others. If you just focus on the image on the top right, we start with actually scrap material. So Simon pointed out in his chart there where a lot of the LCAs and a lot of the energy and CO2 comes from things like mining and the limits that we have on rare earths these days. Well, for us, that's not an issue. We start with actual scrap material, so CNC shavings, turnings, millings, as well as used powder. So we're not taking into effect for our LCA pulling materials out of the earth, because we're actually starting with scrap material. And what we do is we mill it down to a powder that's the size that you want. So if you want 15 to 45, which is the common size particle you have in LPBF, we mill it to that size. If you want an EBM cut to 45 to 106, we can do that. So on the bottom of that chart, you'll see we're actually able to tune the particle size that we want. And because we're starting with scrap in our process, we end up with 100% yield. A lot of the manufacturers, and I'll talk about it in a few slides, they suffer a tremendous yield loss and create waste in their process. And then the last thing is our ability to produce a lot of materials now, because we're starting with a scrap material. We're not reliant on a wire or an ingot as our feedstock. We're reliant on all the scrap that goes on in machine shops and things like that. Just a little bit about the company. We're based in Pennsylvania, just outside of Pittsburgh. We have a 45-acre campus. Our facility's growing. We're expanding this year. We're going to be doubling our capacity. We have 4 systems right now, which gives us about 400 metric tons a year of capacity. That's going to be doubling over the year. And everything we do is recyclable. We actually have several businesses that run under 6K Additive. As I mentioned, we have the powder business. So when material comes into us, as you can imagine, not everything that comes in is worthy of making it to additive manufacturing. We go through about 33 checkpoints along the process before it even sees the UNIMELT for processing, and anything that doesn't meet spec or that we don't think will make a quality powder gets kicked out to another part of our business where we upcycle titanium and other products for the aluminum melt industry and other portions of the market. So nothing goes back into the dirt. We like to think of ourselves as we don't take anything out of the dirt and we don't put anything into the dirt. So it's, as a company, sustainability is kind of core to what we do. And it's interesting, like I mentioned, in 2019, there were a lot of skepticism about scrap. But if you just Google or go to Rolls-Royce's site, as an example, which is what this is from, but it's the same for Boeing, and type in the word revert, you'll see that they recycle 95% of their components out of jet engines. And 50% of that stuff goes back into their jet engines and is used. So it's a very common thing already on the subtractive side. It's just somewhat new to the additive side. So it's not a new concept. We're just bringing it to additive manufacturing, which is key. And then my last slide, then I'll kick it back to Simon, is, this is definitely not a knock on atomization, because they've been a stalwart in the industry. A lot of quality manufacturers here, but their issue is they suffer yield loss. So when they actually put the material through, they actually end up with a wide distribution from 5 microns to 250 microns, and the size that's typically used is 15 to 45. The rest of their material is either sold for scrap, in some cases to 6K, or landfill. If it's titanium, they can't use it again. It's either burned or gone to landfill, which obviously is not good for the environment. So when we compare our process to theirs, we're starting with scrap and we don't create scrap. So it's definitely a unique technology. And the reason I say this is it comes down to the sustainability portion. We contracted with a third-party company called Foresight Management that did an LCA study for us, and this is where we connected with Fraunhofer. They compared our process to the atomization processes for nickel and titanium. And the results, and you can go to our website and download the white paper, the full study on this. For nickel, as an example, which is the one that's shown up here, it's 91% less energy used and 92% less carbon emissions using our powder. So Quality of the powder and atomization, absolutely great. But when it comes to sustainability, there really isn't a comparison between our technology and what we're doing to the atomization process. So with that, I'm going to kick it back to Simon, I think. Does that bring you to your slide? So thank you very much.
Yes. Thanks, Bruce. So this is just a brief overview of what we do at IIT in Aachen, which is where we conducted this study. We do a lot of interesting things, way too much that I could present right here. So if you're interested, come down to our Fraunhofer booth and check that out. So for this study, we used a part by a customer that unfortunately we are not allowed to show you today. But I think what you need to take away from this is it is about 3 kilograms, about a third of a liter. We use 50 micron layer thickness, preheating temperature of the platform 100 degrees. And we took a look at the powder manufacturing process and the LPBF process. We conducted the study on an SLM280, and for this case we only took a look at the electricity, the argon, the powder, and the substrate plate, which of course we are going to reuse. And then there's a second electricity because we kind of connected one logger to the machine itself and then another one to the cooler, which we kind of knew that it would take up a lot of energy. What we got out of the machine then was, of course, the powder that was unused, and then the part on the substrate plate, alongside with the log data that we wanted to generate there. In terms of processing parameters, I think this is fairly standard for Inconel 718. You can imagine if you tweak the parameters a little bit, you end up with a little more or a little less energy consumed. But I think those parameters are a fairly good representation of what all the other machine manufacturers also would use. If we take a look at the raw data for the electric consumption, this is what our data looked like. So it's just the preparation for the build job. So you cannot just go to the machine and hit play. There's some things you need to do in advance in order to set up the build job. And for that, the machine needs to be running at a base load of about 400 watts. And you see the steps purging the machine. Starting the gas circulation. There's a bit of a ramp up as soon as the platform preheating kicks in with around 800 watts. And then at some point, about 40 minutes later, we're able to start the build job. And this is when this returning pattern appears during the print job. It took about 30 hours to print that part. And as you would imagine, these repetitive patterns, of course, correlate somewhat with the layers that we exposured. At the end of the day, we used 46 kilowatt hours of electric energy to manufacture the part and about 7 cubic meters of argon at normal pressure to run the process. We used up 100 kilograms of powder, but of course, since the powder is just 3 kilograms, what we considered to be used here is the powder that was not left in the powder feeder, but everything that's in the overflow and also on top of the substrate plate. Another interesting factor, the build process itself, so really just the machine is about 50 kilowatt hours, whereas the cooling, which is kind of weird, is even 16 kilowatt hours. And you would think there's a lot of room for improvement, because cooling could technically be for free, and you technically don't really need electrical energy to do that. If we take a detailed look at the energy consumption, we found out that for some reason the support exposure takes up more energy, which is a bit counterintuitive, because in that with that specific parameters that we used, the laser power wasn't really higher than at the hatch area. So we don't exactly know what was the reason behind that. But again, you can really see the different steps within one layer in the data that we generated. On the right side, where these two blue graphs are, these are values from literature for it says SLM selective laser melting, but it's of course laser powder bed fusion or whatever you want to call it, and EBM. Those are the values from literature, the range in which they expect one they expect how many megajoules you need per kilogram part, and the red dotted line is what we then measured for job preparation and then the entire job itself. So, and as you can see, this is really at the lower level of what we were expected to use up, and I think still there's got to be some room for improvement, because the machine manufacturers probably by now didn't really thought much about if there's any potential for saving energy. They're more focused on getting good quality parts and very performant machines, but maybe not on how to save energy. If we take a look at the powder on the right side, this is the powder flow chart. So we started out with 125 kilograms of powder that were provided by 6K. Then the green part on top, which is roughly 50% of that, is just what went into the overflow. So we didn't really use it. It didn't really see any action, but we couldn't consider that to be used powder because it was in the process chamber at some point. Then the middle part would be what actually ended up in the chamber. So this is what sits on top of the part inside the build chamber above the build platform. Only about 3.1 kilograms ended up being part. We had about 600 grams of support that, of course, need to be removed after manufacturing. And then all losses together, both in the filter and what we had in sieve residue after reconditioning the powder, that was roughly about 1 kilogram. And then another 22 kilogram remain in the tank, so it was untouched. You can, of course, then divide these numbers in a way you like to get some efficiency KPIs. I think what is somewhat expected is that the second one, that you need a lot of powder, but you really don't melt much of it. This is, I think, the value is very low, mostly because we just had one part in the build chamber, so we didn't try to make it as full as possible. In that case, of course, that number would rise quite a bit. So that was just the raw data that we collected. The question now is, what is the actual impact? And there's different factors you can take a look at. I think the most interesting at this point is probably the CO2 equivalent. So we took all the numbers, took the electricity mix of Germany, and since we've got a lot of coal and whatnot, the impact would, of course, be quite a bit higher in terms of electrical energy compared to, say, Denmark or other countries that have a lot of renewable energy. We ended up with about 12.25 kilograms CO2 equivalent per kilogram part that was manufactured. And again, these other things such as acidification potential and whatnot, we didn't really, or we took a look at that, but I think the most important number is maybe the CO2 equivalent. So just for the LPBF process, we took a look at the primary data, gathered all the information about inputs and outputs, and for this specific part that, again, I cannot show you, but again, about 3 kilograms, we produced about 40 kilograms of CO2 equivalent at ILT in order to manufacture this. Below that value, you can see a comparison of AM and conventional, and this is really tough to do since we didn't go ahead and mill the exact same part and measure the data. But if you imagine a very simple part and you just want to drill one hole, that means your milling machine is not running very long and you don't lose much weight of the part. Compare that to a very complex part where you would mill for hours, you would grind down the part from 5 kilos to just a couple of 100 grams. In that case, AM is, of course, much, much better. So, as always, it depends on the use case. And as last slide for today, we compared the overall CO2 equivalent for that process with that part per kilogram part. And as you can see, the biggest impact by far, as we just learned, is producing the powder, getting the powder from the earth all the way into my printer. This just adds about 10 kilograms of CO2. But really, the biggest deal right here is the powder manufacturing. And if you compare those numbers, oh my God, that moved a little bit. But yeah, as you can see, it's less than 10% if we would go ahead and only use recycled powder, which in my opinion makes a lot of sense. And yeah, with that, I'd like to thank you.
Yeah, so my comment is, first of all, thank you guys for doing the joint project with us, but also the presentation. You know, we've talked a lot, Simon and I and his team, about what's the next thing to do, and we're looking at trying to do the same comparable study for titanium, and then also maybe incorporate the conventional manufacturing of that part potentially into it. So look forward to that. But also, you know, I'd like to take it even further, which is now take the used powder that you have, bring it back, have it recycled at our thing, and bring it back in for another part later on, which would be a much comprehensive study, but there's lots we can do. But this has been tremendous to work with these guys. And again, for us, you know, we hope you guys understand the value of actually using recycled powder or powders that come from scrap. There are a few others out there that are doing it, and again, I'd love to think that you're just going to use ours, but I would, whether it's ours or somebody else's, I think the value of used powder and recycled powder, if it's done correctly, adds a lot to the sustainability quotient for your company. The other thing too that we're looking at as a company is being able to assign a carbon credit value. We wouldn't be a carbon credit, but if you use our powders, what would that equal in carbon credit? So if you're using that, your company would be able to buy that much less carbon credits by using our powders. So I think we're running a little bit over, so I'm going to wrap up and say thank you, Simon, very much. I appreciate it. Thank you, everybody, for listening.
Thanks.